Hello, everyone. My name is. Uh, okay. Hello, everyone. My name is Harsh Agarwal, and I belong to the Singapore University of Technology and Design in Singapore and the Changang University in Taiwan. Today, I'm going to present on the topic towards artificial intelligence chips design, a ground-up approach for beginners integrated circuits design education. I work in the research group of Professor T. Huitio, who belongs to the SATD in Singapore. Okay, moving on to the presentation, I'll start with the outline. First up, there's the motivation and the problem statement for the study, and then I'll discuss the architectural overview. The implementational details will be discussed after that. Then there will be a slide mentioning the results, and then finally the conclusion. Okay, so moving on to the motivation for our study. So this tutorial study is actually aiming to simplify the AI chip design process for beginners in the IC design field, and it's doing so by focusing on the XOR classification problem, and that uses an artificial neural network. The reason behind this kind of study is that it's often observed that beginners in this field often struggle to grasp all the underlying principles which are important for hardware design, and especially for AI applications. As just mention as to what is the XOR problem. So the XOR circuit basically checks for dissimilar inputs, and due to its input-output distribution or the truth table of the XOR circuit, it cannot actually be solved by a single layer perceptron. Okay, so moving on to the next slide, I'll talk about the uh, model architecture now. So if you see the first diagram, which is the MLP architectural diagram, so it consists of two input neurons, which is shown by X1 and X2. Then there's one hidden layer with two neurons, and then there's an output layer which solves the problem. And if you look at the feed-forward equations, the equations where y1 and y2 are getting calculated, as well as xh1 and xh2 are getting calculated, those correspond to the first layer or the hidden layer of the network, and then YH and ZHC correspond to the output layer. Also, the activation function which has been used in this particular network is the hyperbolic tangent function. And in order to do the training, we first do the feed-forward output computation, and then we calculate the backpropagation equations, which will be used to update the weights in the biases and also to minimize the error in the process. So, moving on to the next slide, which talks about the parameter tuning. So, the equation 2 basically outlines all the backpropagation equations for the different parameters in this network. So, the parameters WH1, WH2, and BH, those are the parameters which were uh, corresponding to the output layer, and then the parameters which are like from W1 up till B2, those are being calculated by further using the chain rule of differentiation to calculate the parameters until the first layer or the inner layer. So in order to do this parameter tuning, first of all we do the first pass or forward propagation. This is done using randomly initializing the weights and biases, and a fixed seed number is used for this. And then in order to calculate the backpropagation, first we need to calculate the error of this network. We use the mean square error in our network for this estimation, and then the backpropagation equations, which are shown by equation 2, are calculated using the chain rule. Okay, so next up we'll move on to the system or the software implementation. So if you look at the figure 2, which is basically the loss versus the learning rate graph. So it can be observed that the global minimum basically, or the least loss for the uh, different learning rates is observed in the range of around 1.0 to 1.3 or 1.35. So this basically helps us to determine that the optimum learning rate will be in this range. And then furthermore, we do the uh, the loss versus the epoch graph, which can be shown in the second basically graph. So we do so over a long uh, like uh, 2000 range, uh, 2000 number of epochs. So this helps in confirming that there are not there's stability in the outputs, and through this we determine that the 1.2 learning rate is optimal for our use case. So just to mention what is being done in this step. So the learning rate is actually tuned using the brute force technique, and 1.2 shows the best results. For our brute force technique, we swept the values from 0.5 up till 2.0, and we did so in regular intervals to obtain the best performance. And we capped the number of epochs or iterations to 2000. And once we determine the best learning rate, we do the training and obtain the final weights and the biases for our further implementation or the further hardware implementation. Now, moving on to the hardware implementation, we'll see that the first uh, step actually, or the first determination which we need to do for our hardware implementation is the determination of the approximation technique. So if you look at the equation 3, the approximation equations have been outlined in that equation. So in order to, for our use case, we basically use a very simple approximation technique where we uh, take for whatever input values which are say less than -2, we approximate the output to be -1. And if the values are greater than 2, we do so the approximation is a 1, and all values in between those two ranges, or the range of those two values, we just divide the input by 2. So on the surface this can look a little simplistic, but the this particular technique for approximation actually uses very simple or basic shift operations, and this actually helps in reducing the computational complexity to a great extent. When we do so, we actually make this model very resource constrained, environment friendly. So it is maybe more easy to use this model for deployment on FPGAs. And the graph actually shows that using this approximation technique, actually the approximation closely matches the original Danish curve. So the loss of accuracy is quite minimum for us. Then in this flowchart, I've outlined all the hardware design steps which I followed. So in order to start with our hardware design process, quantize the weights and biases which are obtained from the training process into Q3.2 format. So the Q3.2 format basically corresponds to one sign bit and then three integer and two fractional bits. And the output of the design is quantized at Q9.6. So if you look at the flowchart, once we determine the Q3.2 weights, we multiply it with the inputs of the XOR gate, which is zeros and ones. And then after the multiplication, we are adding the biases, which changes the quantization to the Q5.2. And then we do the activation function implementation for the first layer. Similarly, once the activation function is added implemented for the first layer, we do the implementation for the second layer, wherein we similarly add multiply the activations with the biases, with the weights, and then add the biases to those multiplications, and finally do the final tangent approximation. That final tangent approximation is in Q 9.6. So this entire design was synthesized and tested using Verilog, and it was done in the Google Colab environment. This particular graph or this particular diagram shows the schematic for the implementation. So the left hand side shows the first layer, and this right hand side shows the second layer. The first layer consists of muxes which represent the multiplication step, the biases which represent the adders, and sorry, the adders which represent the addition of the biases, and then the comparison shifters which do the activation function implementation. And similarly, the layer 2 has multipliers and adders, and also the shifters for the output layer implementation. Finally, moving on to the results slide. So, Verilog simulations validate that the hardware design, which has been implemented in the study, actually completely corresponds with the XOR truth table. So, if you look at the figure 6 and look at the different inputs for the XOR gate, Uh, so if you look at the case where the inputs are dissimilar, we get the output of 64, and when the inputs are similar, we get the outputs of minus 64. So in quantization format Q 9.6, 64 is actually plus 1 and minus 64 is minus 1. So when you look at the figure 7, the plus and minus 1 actually help us in understanding that the Verilog results and the ideal XOR results completely match. So we get good results for our implementation, and we are able to map the XOR ANN circuit into the hardware. Okay, so just finally concluding whatever I have mentioned in this study. So the presentation covered designing an AI chip using a simple neural network for XOR classification, and the network architecture, the training steps, and the hardware implementation were discussed. The usage of TANH activation, backpropagation, and Verilog implementation ensures that comprehensive coverage of the entire chip design process was presented. And future research directions for our study is basically to move the study to more complicated networks, and also extend the design to say use some sequential elements. We're also looking into exploring new activation functions and other quantization techniques. That will be the end of my presentation. Thank you, everyone.